Hello everyone, my name is Muhammad Hassan and I'm going to talk on the title of Lanthanide in organic synthesis. The outline of this talk consists of introduction, scope of lanthanide in synthesis, organocerium reagents, samarium, two iodide catalyzed reaction, and selective examples of enantioselective selective lanthanide catalyzed reaction, and at the last summary of this talk. Let's have a look on introduction first. Lanthanide firstly introduced by Victor Goldsmith in 1925. They are also called as inner transition elements, rare, or you can say rare earth elements are metals placed in the sixth period of the periodic table, consisting of 15 elements, having the atomic number range from the 57 to 71. They predominantly show +3 oxidation state, but sometimes they show +2 and +4 ions in the solution or in solid state. Except promethium, they are non-radioactive. One of the important terminology regarding lanthanide is lanthanide contraction, and lanthanide contraction is the gradual decrease in the atomic and the ionic size of the lanthanide with the increase in the atomic number, and it may be due to the as the atomic number increases, the positive charge also increases, or you can say as the atomic number increases along other thing decreases, or atomic radius or the ionic radius greater than the screening effect. What will happen actually? The last coming electron enter in the this 4f orbital, which is very far away from the valence shell, and due to this shielding effect, it does not work, and attraction effect of the nucleus work, whereby the atom gets contracted. If you see here, with increase in the atomic number, the size of the lanthanide metals decreases. Scope in organic synthesis: the importance of rare earth metal salt as a catalyst is growing rapidly based on their unique chemical and physical properties. They adopt +3 oxidation state, which is stable and not easily changed to the other oxidation state under normal conditions. Reactivity can be controlled by two methods. The first one is the fine tuning of the structure of ligand, and the second one is changing the center metal since appropriate ion size and the structure can be selected from the series of the lanthanide based on the lanthanide contraction. And the next one is the fine tuning of the ligand, and the selection of center metal result in various application of the rare earth metal as the catalyst in the number of catalytic reactions. Various organic reactions including catalytic asymmetric reaction can be performed using rare earth metal based the Lewis acid not only in the organic solvent but also in water. Now I'm going to talk firstly about the organocerium reagents. We can prepare the organocerium compounds by transmetallation from the organolithium or Grignard reagent. When we treated the alkyl lithium with the cerium chloride, then we will obtain organocerium reagents in the presence of THF and -78 degrees Celsius temperature. Reaction of organocerium, they act as a weakly basic and the strong nucleophile. Whenever we want to introduce the bulky group on the hindered carbon center, we can use organocerium reagents. They show highly regioselectivity toward the alpha beta unsaturated ketones 1 to 2 addition. Let's have a look on the example first. When we treated this starting material with the N-butyl lithium in the presence of THFM -78 degrees Celsius, we will get this compound. And if we want to insert N-butyl on the carbonyl group, we have to use organocerium compound, and we will get this compound. And you can see, and we introduce the bulky group on the hindered carbon through 1,2 addition, and we utilize the organocerium reagent in this case. In the second given example, in the case of Grignard reagent, if the alkyl group is bulkier, then it acts as a base rather than act as a nucleophile. It abstract the proton from the alpha position and result in the formation of the enolate. And then That inolate react with the remaining starting material and result in the formation of the mixture of the product. One is the minor product and the second one is as a major product. And if we want to synthesize this one as a major product, then we have to use the organocerium compounds or organocerium reagent. What will happen here, the isopropyl is added to carbonyl group through 1,2 addition, and we will get this as a major product. And this third example, the case of the third example is same as the previous one. Another important feature of the organocerium is the chelation. Chelation in the reduction of the carbonyl group, chelation can cause a reverse stereoselectivity. You can see here when we simply reduce, we will get this one, and when we reduce by using sodium borohydride in the presence of cerium chloride salt, then the stereochemistry totally change from this one. Now, samarium is one of the popular element in the lanthanide series regarding to organic synthesis. It is known as a Kagan's reagent when applied as a solution for the organic synthesis. It is a strong one electron reducing agent that is used in the organic synthesis. We can prepare the samarium iodide by direct reaction of the samarium with the iodide, or by reacting the samarium with the diiodide, or by reacting the samarium with the alkyl iodide, typically generated in situ, and most stable oxidation state for the samarium in this case is +3. It is used for the reduction of the various functional groups. We can reduce the carbonyl into alcohol, we can reduce the alkyl halide, we can reduce the alpha functionalized carbonyl compound into the desirable products. In the case of the reduction of the alkyl halide, in the presence of the samarium iodide, the halogen atom of the alkyl, alkenyl and the aryl halide is replaced by the hydrogen. In tetrahydrofuran, the mechanism of the alkyl halide reduction likely proceed through the radical intermediate, and the hydrogen abstract from the solvent in the last. And in the case of the aldehyde and the ketone reduction by the samarium iodide is primarily based on the mechanism elucidated for the similar one electron reducing agent. Upon the single electron transfer, ketyl dimer 4 form in the absence of the protic solvent. This dimer collapses to form the 1,2 diols. In the presence of the proton source, however, the dimer may undergo either disproportionation to form the samarium alkoxide and the carbonyl compound, or protonation to form the carbinol radical 2, followed by the second reduction of the protonation yielding an alcohol. In the case of the reduction of alpha functionalized carbonyl compound, this process may initiated by the initial electron transfer to either the substitution at the alpha position or the carbonyl moiety. Two pathways depending on the relative electron affinity of the functional group, and the second reduction immediately follow, after which the either proton or the elimination tautomerism afford the final product. In the case of the nitro group, reduction may be reduced to either hydroxyl amine or amine oxidation level with the samarium iodide depending on the condition employed. Electron transfer followed by the proton transfer and the elimination generate an intermediate nitroso compound which undergo 2 more round of the electron transfer and protonation to afford the hydroxylamine. Further reduction of the hydroxylamine led to the imine formation. Here are some examples of the samarium iodide catalyzed reaction: reduction of the conjugate double bond, deoxygenation reaction of the epoxide, reduction of the carbonyl derivatives, alkylation by the alkyl halide, and the coupling of the organic halide, in which we form the carbon-carbon bond linkage actually. We can perform the cyclization by using samarium iodide radical phenomena. It is unclear here which pathway is used for the addition to the carbonyl. Two possible pathways may be samarium barbier and the samarium grignard. In first case, separate radical formation occur, which later combine, and we will get the final product, alcohol. And in the case of the samarium grignard, this directly added to the carbonyl after, and we will get the final product after protonation. In this case, the final product, which is the major product, follow the samarium grignard pathway with the 89% yield. Let's have a look on some example of the enantioselective lanthanide catalyzed reactions. The conjugate addition of the nucleophile to electron poor alkene play an important role in the organic synthesis by allowing carbon-carbon and the carbon heteroatom bond forming reactions to be easily achieved. The addition of the dimethyl malonate to the alpha beta unsaturated and tosylamine occur through the lanthanide triflate in the presence of the chiral ligand, and we will get the E form of the product and the Z form of the product. The result indicated that the preference of the dimethyl malonate to attack from the psi phase of the double bond of the unsaturated imine, the mechanism involved an octa coordinated lanthanum species with the both 1,3 dicarbonyl compound and the imine coordinated to the metal center. In this complex, the imine in its S-trans conformation was oriented to avoid the steric interaction of the aryl and tosyl group with the phenyl group of the ligand, thus leading to the Michael product exhibiting the R configuration at the stereogenic center and the E geometry at the double bond. In Michael addition of the nitromethane to as a chalcones and other alpha beta unsaturated ketones occur through the lanthanum triflate in the presence of another chiral ligand in the which is responsible for the stereochemistry of our final product. Stereochemical model illustrated that the attack of nitro group occurred through the psi phase, and we will get this final product. In case of 1,3 dipolar cycloaddition of aromatic aldehyde with epoxide catalyzed by gadolinium triflate in the presence of chiral ligand, and we will get this as a final product. The transition state shows that gadolinium coordinated to all oxygen atoms of the ligand through a tetrahedron manner. The catalyst also coordinated with the oxygen atom of the carbonyl group in epoxide that led to the formation of the corresponding carbonyl yield, and an hexa coordinated gadolinium derived intermediate was generated. The oxygen atom of the aldehyde attacked the re face of carbonyl yield because its psi face was shielded by neighboring 2,6-diisopropyl group of the ligand. Then ring closure occurred to afford the final product. In 1,3 dipolar cycloaddition of aromatic aldehyde with azidrine occur through neodymium triflate in the presence of chiral ligand, and we will get this one as a final product. This mechanism shows that the attack occurred through the rephase, as in the case of the gadolinium catalyzed 1,3 dipolar cycloaddition reaction. These three examples show various lanthanide catalyzed aldol reaction and the Mukayama aldol reaction in the presence of different chiral ligands which are involved in the determination of the stereochemistry of final products. In some cases, counter anions of lanthanide salts decrease the yield as well during Mukayama aldol reaction. We can perform the epoxidation and the manic type reactions as well by using the lanthanide as a catalyst. In summary, we can perform the lanthanide catalyzed reaction in the mild condition, and they tolerate the wide range of the functionality. Their activity can be manipulated, allowing each step in the sequence to be tuned. Moreover, rare earth metal based leviases, mostly rare earth metal triphletes, are the novel catalyst series from which we can select the most effective metal that has appropriate size and the structure for the organic synthesis. Owing to their high coordination number and the hard acid character, fine-tuning of the ligand is also possible. Various multifunctional bimetallic catalysts have been developed thanks to these characteristics. In addition to above all, rare earth metals based leviases are compatible with the water. This property is largely different from that of the traditional leviases such as aluminum chloride, titanium chloride and the boron fluoride, which need strictly anhydrous conditions. However, there are some limitations of lanthanide catalyzed reactions. Many of the lanthanides and the other rare earth elements are prohibitively expensive, especially for the large scale and the stoichiometric reactions. In addition, since they contain the rare metals, the production of these reagents may itself be a polluting or hazardous process. Thank you so much.